What we want to talk about is in chapter 26, which is on current and resistance. Okay, and so what we have is that our electric current is the flow, or really it's the rate of charge through some region. Okay, and the usual way that we take a look at this is that we have some conductor. Usually draw kind of a wire, is what I'm envisioning here. So I got my conductor. And then what we're going to watch is we're going to watch some sort of cross-sectional area. Okay, and we're going to determine the net amount of charge that crosses through that area in a given time. Okay, and so then that's going to be that will constitute our current. Okay, now one thing to note is that in a standard conductor, what you have is that the charges that are free to move are the electrons. And they usually refer to those as the conduction electrons. Okay. And the way I always picture it is I usually picture my little springy box, which is at campus, and so I don't have it. But the little atoms sit there and they wiggle in place like little kids on sugar, trying to sit still in seats. And as they knock into their neighboring atoms, they interact through their outer electrons. And in a conductor, you have loosely held outer electrons on the atoms, and due to their thermal motion and their interaction with their neighboring atoms, you can, kick some of those electrons out of their particular atom. Now, the electrons will remain bonded to the material, but they are no longer bonded to a particular atom. And those become our conduction electrons, and we can move them, quote unquote, freely throughout the conductor. Okay. Now, one of the things to talk about when we talk about our little conduction electrons is that the motion of these electrons is, fairly random. Okay, due to the thermal motion. So they zoom this way, they zoom this way, they zoom this way. And as they, change directions, they have interacted with an atom or another electron. And actually, it's a lot more complicated than this because, what can happen is it can get, knock into an electron and then fall into an atom. And then the other electron takes its place, zooming around randomly, kind of things like this. Okay. And so then what we get is that the average velocity of this kind of random motion on the electrons, in the absence of any kind of electric field, the average velocity is 0. So on average, it goes nowhere. Okay. But if you go in and you look at the magnitude of the velocity, then it's going to be on the order of like 10 to the 6 meters per second due to its temperature. Okay. And so okay, so in the absence of an electric field, your average velocity is 0, but it's moving very quickly. as it goes on average nowhere. You know, zoom, 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 and it gets nowhere kind of things. Okay. Now, if we were to go in and apply a potential difference across the ends of the conductor, then what this will do is this will establish an electric field down through the conductor, essentially at about the speed of light. Okay. So then this will then cause there to be a force on our electrons. And so then once we apply potential difference, across the conductor, then we will go ahead and establish an electric field down through the conductor. Like I said, we'll establish this essentially at the speed of light. And this is going to exert a force on the electrons. Okay, so if we picture that I have some sort of electric field down through the conductor, so that's our electric field, and then I have this electron here, then what we get is that since the electron is negatively charged, there will be an electric force that will be in the opposite direction of the electric field. Okay. And this is just by the fact that the electric force is Q times the field. Okay. And so when the charge is negative, it'll reverse the direction of the electric field vector to produce the electric force vector, the direction of it at least. And so then what this will do, this will then cause the electron to accelerate in the direction of that force. This is due to, Newton's second law. That what you get is that the net force is equal to the mass times the acceleration, or that the acceleration is the net force over the mass. Okay. And so this will cause the electron to accelerate. And so now what you would think is that, well, it should end up going, faster, faster, faster down along the length of the conductor. But that isn't really quite the case. Okay, because what's going to happen is that as we go in, then the electron is still zooming randomly around. Okay, still zooming like this, and then zooming over like this, and zooming down like this, and then up like this, and over like this, and up like this, back like this, and up like this, and over like this. I mean, still going randomly at fairly high speeds. But then what you pick up is that your average velocity is going to be fairly slow down along the length of the conductor. And this velocity is often referred to as either the drift velocity or the drift speed. And it's on the order of like 10 to the minus 3 meters per second. Okay, but it's still interacting with all the atoms and molecules as it goes along. And in my mind, this is kind of like, accelerating downtown, right? So the light turns green, you hit the gas, you speed up, and then you stop at the next stop sign. And then you hit the gas, you speed up, and then you stop at the next red light. And you hit the gas, you speed up, and you stop at the next stop sign. So you don't actually end up going faster, faster, faster as you go. Each of the stopping at the stop signs or stopping at the red lights is essentially the electron interacting with one of the atoms or molecules in the conductor itself. And as that electron like slams into the atom, it causes it to vibrate faster. And the bigger the vibration of the atoms and molecules, the higher the temperature of the material. Because the temperature is a measure of the average kinetic energy due to that random thermal jiggly motion of all the particles that make up the material, make up the matter. And so what we've done is we've taken the energy and the work done by this electric force, and we've converted it into an increase in thermal energy of the little atoms and molecules within the conductor itself. Okay. All right. So now what we need to talk about is we need to go in and talk about essentially what we call the conventional current. Which we're only going to call current. Okay, so when we talk about the conventional current, then what you get is that with the conventional current basically tracks the motion of the positive charges. And you're like, but the electrons are the ones that are moving in our standard conductor. And I'm like, yeah, that's an unfortunate kind of thing, you know. And unfortunately, it can be traced back to a choice that was made by Franklin when he was working to study electricity, you know, the big key on the kite kind of thing in the thunderstorm type of idea, okay, is that he was studying electricity, and so he made a choice as to which charge was positive and which one was negative. Now, we really shouldn't blame Franklin. He didn't even know there were atoms, much less electrons. Okay, so this was just a choice that was made in his experiments in, you know, electricity, you know, which is in this case charge. And at that time, they either had, I can't remember if they did a 2-fluid model or a single fluid model for electric charge. You know, so what you have is that if you have an excess of one fluid, that would be positive, and an absence of that fluid would be negative. Or you could have a positive fluid and a negative fluid, just like we have positive and negative charges. You know, so I mean, at that time, like I said, they didn't even know there were atoms. So it's really hard to blame them. But what we talked about with conventional current is that it tracks the motion of the positive charges. Okay. And so what we're going to do is we're going to take a look at the little simple argument. So if we go and we start off with some positive and negative charges in some kind of configuration. So I'll have one of each on the left, and I'm going to have one of each on the right. Okay. And then what I'm going to do is I'm going to go in, I'm going to move this positive charge to the right. Okay. And so when we move that positive charge to the right, what we end up with is we end up with 2 positive charges on the right and 1 negative charge on the left. And we look at the net effect, then really what we ended up with was a minus on the left and a plus on the right. And by moving the positive to the right, this is the direction for our conventional current. The conventional current, or the current, would go to the right, because that's where the positive charge moved. Now, if we go in and reconsider, but in this case, we're going to move the negative charge, because in a standard conductor, that is what moves. Okay. And you would think that, oh, maybe we should, you know, redo the definition. And that's possible. But I think what we also should keep in mind is that, you know, when you look at the entire universe, the most common state of matter is, or for, you know, visible matter, is plasmas in the stars. And so they're actually not standard solids like we would see today. And so what we end up with is, in moving the negative charge to the left, is we end up with the same configuration as we had when the positive charge moved to the right. So having negative charges move to the left is equivalent to having positive charges move to the right. Okay. So So then what you have is that when you actually have negative charges that are moving, the conventional current just goes the other way from the motion of the negative charges. Okay, so it doesn't really matter if we are talking about, tracking the positives or tracking the negative types of things. Okay, and so then what we can do is we can go in and I can redraw out my little conductor. Again, I picture it as a wire. Usually draw it as green because I kind of picture it might be copper, and copper patinas as green. And so then we're going to attach this through a switch to a battery. Okay, and so then this battery is going to have some ideal voltage. Let's just say it's like, I don't know, 9 volts. So 9-volt battery. When we close the switch at t equals 0, they're going to place a potential difference across the ends of the conductor, and that's going to essentially establish our electric field down through the conductor. This is going to be the high voltage side, this is going to be the low voltage side, and so then our electric field is going to run, as it usually does, from high to low. Okay. Now, what we can do is we can go in and identify our little area. So this is usually taken to be a cross-sectional area through the conductor. And while technically it is the negative charges that move, I'll probably just draw it as the positives moving because, negatives moving left is equivalent to a positive going right. And what we'll get is that we're going to have these positive charges that are then going to go in and move through this surface, and therefore count as the amount of charge that has went past this point in a given amount of time, which is going to constitute a current. And you have to worry a little bit about the fact that it should actually be the net charge. So if you get so many positives going this way, but other positives went the other way, then those cancel off and give you less current, kind of thing. So it really is net charge through that cross-sectional area per time. Okay, and it's kind of like, oh, you went to the side of the highway and we counted how many cars went by at a certain point to get the rate of traffic flow, kind of like a current. Okay, only this is, of course, charge, of course. And so then when we go and we define our current, what we get is that the average current is the total net charge that went through this area in a given amount of time. You can tell it's the average because of the bar across the top. There's our net charge per time, like this. And it's the net charge, let me say, the charge that crosses through the area. Okay. And then what we can look at is we can also write down that this means that the instantaneous current, or the current, would be the time rate of change of the charge through the area. So then this is just our, again, we don't say the word instantaneous, just like we don't say the word conventional as the, the derivative of the charge per time. Okay, our standard rate. And then if we go and we look at our units for the current, Then those are the units of charge, which are in coulombs, over the units of time, which are in seconds. Okay, and then this is kind of an interesting little point that we get, is that this combination is an ampere, but that's not really quite correct. Okay, because what we find in the SI units, in the International System of Units, in the SI units, what you get is that the second and the ampere, these are base units in SI. Now what you have is that the coulomb is actually a derived unit. There are 7 base units in the system, and all the other units are some combination of those 7 base units. And so a coulomb is an ampere times a second. And the reason for this is because it was very difficult to measure charge, but it was much easier to measure current. So they defined the base unit in the system off of the ampere. So I mean, like I said, it seems like it's wrong because really the charge is the fundamental property and the current is not, but yet the unit for current is essentially fundamental in the unit system. So you get that a coulomb is an ampere times a second. Just a funny little bit thing. Okay. All right. And so there we go. So that's our current. And so very often what we will do, I need to make one other point that's important. And I think I mentioned this before. At least I hope I did. Maybe not. No, I think maybe not. So current is not a vector quantity. Now it is directed. It goes in a particular direction, right? So since the positive charge is moved to the right, then our current goes to the right through this conductor, okay? But current is not a vector quantity. If we go in and we look at a circuit piece, and we have a junction. So this is going to be a junction in a circuit. So we have our wire segments, they would continue on. I didn't draw anything but just at the junction. So those are supposed to continue on. Then what we can have is that the current will flow into the junction on this upper wire segment. Let's call it I1. Current will flow into the junction on the lower Y segment. Let's call it I2. And what you get is that the current then flows out of the junction along the horizontal wire segment. Let's call it I3. And then what we'll have is something called Kirchhoff's junction rule. Will basically state that what you get is that the current 1 plus the current 2 should equal to the current 3 because charge is a conserved quantity. The charge that goes into this junction has to equal the amount of charge that goes out of the junction at every instant. Now, have you ever seen 2 vertical vectors add to give you a horizontal vector? Well, no, because that's not how they work. Are we all good? I didn't get an answer to that, so maybe I should be concerned. Are we good? Okay. Marina says she's good. Really what I need to know is anybody's not good. And that's really a hard question to ask because nobody wants to answer that one. Oh, no, it's not good. So that's a hard thing to state. So, all right. There we go. So, now, what we can do, and to make matters worse, is that we could redraw the circuit. I could bend these wires this way and that, and it still doesn't change the junction rule at all. But if they were actually vectors, we would do, X components and Y components, you put Y's with Y's, and you put X's with X's and things like that. And so, this can't be a vector quantity, okay? And so hopefully that was a good enough argument for why it is not a vector quantity, even though it really seems like it should be because it has a direction. So what I say is that it's directed, but it is not a vector. Okay. All right.